Welcome again, everyone, to Top Educators' Secrets for Creating Star Students here on February 7th, 2014. You can see the title here. Our main presenter, and he'll have a colleague with him today, is Dave Wilson. He's the Director of Academic Programs at National Instruments. Now on the next slide, you can see both Dave and his colleague, Mark Walters. Dave, your title is Director of Academic Programs. What do you do there at NI, and how did you get started, by the way, in all of this, if you don't mind me asking you that question?
Well, it started many years ago. In fact, this is my 23rd year with National Instruments. I started in industry where I was working with controls and automation and measurements with the U.S. automotive engineering community. And about 5 years ago, I was fortunate enough to get involved with bringing a lot of that experience now into the education realm, where we're working with educators to help them get students prepared to go out and participate in industry. So I really got I got started in all of it through industry and seeing what was happening out there, and then by having an opportunity here at National Instruments to put that together in reaching out and working with our products and with educators.
Well, good. Thank you, David. That wealth of experience, I think, really shows as you'll be going through your presentation today. And also joining you is your colleague, Mark Walters. I've known Mark for a number of years. He's the Academic Marketing Manager at National Instruments. What does that mean, Mark? What do you do at NI? And by the way, how did you get started as well?
That's a great question, Mike. I've been working with National Instruments a little bit less than Dave, only 8 years. But my key focus is to promote our educational solutions that will help prepare students for industry. So I work with a number of universities and colleges throughout the United States, Canada, North America, and South America to provide better learning solutions and promote the use of tools that will help prepare them once they graduate and go into industry and research.
Well, thanks, Mark. You know, I have to admit that my experience with NI has just been, I think, impressed in a way by your focus on learning and what happens in the lab, what happens in the classroom. So we appreciate that. Dave, I'm going to turn over to you now. Why don't you take us forward? You're in control of the advancing, and the floor is yours.
Well, thank you, everyone, and thank you for joining us. So we wanted to start out with what we were going to talk to you about today and things that you can look for throughout the presentation. And we're going to reveal top educator secrets for producing star students. We'll talk about some of the things that we've come to realize, how technology can play a role, and how educators working with companies like National Instruments have been able to put things together to produce students who are ready to go participate in technology and industry. And also we're going to talk about answering the challenges to increase industry-ready students, some of the types of things that they're likely to see, and some of the techniques that we've seen are things that they can employ to go out there and be ready to participate and to gain employment in the marketplace. So I'd like to start a little bit with National Instruments and tell you a little bit about our company. So National Instruments is a company that has a mission statement, as you see, and we say that we equip engineers and scientists with tools that accelerate productivity, innovation, and discovery. And so this ranges from I/O boards that allow voltages to be measured out in the real world and things like temperatures and pressures to be converted to voltages and then measured, all the way up to controlling things like nuclear reactions, and even finding things like the Higgs boson, which you may recall was out in the news here in 2013. And in fact, even some rocket science. We work with SpaceX, and we provide a lot of the tools that they use to test their rocket ships and also to have the user interfaces in their command and control centers. So National Instruments makes the tools that scientists and engineers use to build their test systems, their control systems, their experiments, and that technicians use out in the world on a daily basis. So that's a little bit about our company at National Instruments. Another thing that's very interesting about National Instruments is the breadth of areas that we serve, and that's represented largely by the number of companies that we interface with. In fact, we show a few of them here in this slide, but we talk about serving over 35,000 different companies. And one of those companies might be a company like General Electric or Toshiba or Ford Motor Company or 3M. Now each one of these companies could have dozens or even thousands of installations of our products from our LabVIEW called software, our software called LabVIEW, and then also all the I/O products that we make. So there's literally millions of applications that scientists and engineers and technical people, technicians are using around the world to actually go and get their jobs done. And National Instruments is a big part of that. So as we get started with our discussion, I thought it might be good to take a little bit of a look back into very recent history and some of the amazing things that have been happening around the world. So let's start with SpaceX, and I've mentioned that SpaceX is someone that we work with, and here's a picture of their Dragon capsule. And this is a public-private partnership in some ways, where it's really a private industry in SpaceX, but working with places like NASA, who of course we know is public, and they are reaching out to expand frontiers in space. Well, National Instruments, of course, is a big part of that, as we make the tools that they use to test the pressurization of this. They make the tools for communication, and also we make the tools that they're using in their command and control centers. Now, that's sort of on the space in the out there picture, but you can look at a very small element, which is this thing called the Higgs boson. And you may or may not know, but there's been billions of dollars, I think in the $7 to $10 billion range, where they built something called the Large Hadron Collider. And the Large Hadron Collider was all about getting enough energy when you take small atomic and subatomic particles and you accelerate them and break them into pieces, and then you look for things that are inside that can explain the world. And the Higgs boson was something that was theorized by a scientist named Mr. Higgs, and he actually said if we can find this, we'll understand what gives particles mass. Well, what's important about all of this is that the tools that are used to get this done are used by technical people and technicians and technologists, as well as scientists and engineers. And we've made the technology that allows those beams to be focused so the particles can actually collide in giving pieces. So that's sort of the spectrum. And then one other thing I thought that was worth mentioning is a little bit about communications. And now we know that our smartphones give us great information, but we'd like that information faster and faster. So the 5th generation or 5G wireless technology is coming along, and National Instruments is very involved in making products that let engineers and even scientists in this case go and try out their new techniques and their new technologies to see if we're going to be able to bring this next generation of wireless technology to cell phones that we will use every day. So when you take a look at National Instruments' position in all of this, we work from academia, and we're trying to get the tools and the technologies into students' hands so that when they start and they're doing engineering and they're doing technology in the academic space, it's going to take them out to being ready to participate when they get out in the world. And as our talk today, we'll make some observations on some of the things that are preparing them to do that and the way that we're trying to help educators better be prepared as well. So I like to start with equations, and the reason I do this is because equations have been around for a long time. I often wonder if the equal sign is not perhaps man's greatest technological achievement, that you can actually say that one thing is equivalent to another. And think about the implications when Einstein actually came up with E equals mc squared. And in a sense you could look at that and say, yeah, well, that's just another equation. But what we discovered, of course, is that the implications that some of those numbers were extremely large, and that led to this whole idea of nuclear fission and production and capability. So it exposed a tremendous amount of power that were put in the hands of the world, and this is just one little example. But when students come to us and they're entering into colleges and universities, they're asking the question, how is all of this relevant? And maybe you've heard the question before, when will I ever use this? But when you look at equations like this is what they see, and it looks like a bunch of abstracted stuff that really doesn't have a lot of meaning. So in my years working out in industry, what I discovered was we actually gain a relation with these equations, and we bond with them in a way that gives us ways to look at these that we can appreciate. And I'd like to give you a real quick example. That bottom equation is a control equation, and it looks just like a bunch of numbers. But on the other hand, it is the fundamental elements that are used by people nearly every day in their automobiles in cruise control. So when you're going to actually implement cruise control in a vehicle, you would need to know this equation. So when somebody who's worked with this for many years look at this equation, it's not an abstract concept. This conjures up many images of many experiences that they've had with this equation, and they really begin to appreciate it. One story I like to tell is that I worked with 3 students from the University of Texas, and I was very interested one summer in developing an electric bicycle. And an interesting thing about an electric bicycle is that it has a motor, it's got a battery power source on it, and if you introduce a small processor in the middle of it, you can begin to take the throttle and say, well, here's where I'd like the speed to be, and then you can have the controller get in the middle of it and actually determine what it needs to do to get you to that speed. And that's much how your cruise control works. Well, here's the interesting thing. When we put this in the middle and we started to set up the equations, we had to set values for this K, P, Ki, and Kd value. Well, you set numbers for those, and maybe you take guesses at first. And if you get those numbers wrong, then you see how the equation reacts to the situation, and I can tell you, it reacts in a way where it's surging you forward and slowing down and surging you forward. Now, if you happen to be on the bike at that particular point in time, that's called bonding with the equation. And so now you're very, very tuned into what those parameters mean and setting of those equations, and it has much stronger meaning. So in producing STAR students, being able to relate to the equations is critically important. So we have broken down some of the approaches that we've seen as we work with educators into 3 areas. And the first area is reaching out to the students themselves. So you actually want to be able to go and interest students into technology and into science and then into engineering. And one of the things that I would like to point to is FIRST. Now, we all know that Dean Kamen has put together an incredible program. He and Woody Flowers have done amazing work. And this does a real nice job at reaching out to students. But even as great as that is, reaching out to students, there's great numbers of students out there that can and should be interested in technology, science, and engineering. And so the outreach part is critically important to them. And in fact, I find, and I think many find, that children and students are naturally interested in the types of things that we see that are happening, like cars and wind turbines and agriculture. They're typically interested in those. So the outreach part is very critical to show them that studying technology and studying science and studying engineering, these things will allow them to actually continue with the interest that they've had as very, very young children. But once you get them there, the next step comes into play, which is critically important, that you need to be able to retain them and work with them so that they will continue and then ultimately be ready to graduate, which is the 3rd step, and then go out and productively contribute. And one of the things that we find, which is very important, is that students need to be able to go out there and demonstrate to prospective employers that they've gained the kind of education that is not only interesting and relevant, but also very tangible in their abilities to go and participate and contribute to what that company would hire them to do. And the sooner that they can do that as students, the more likely they're going to be to get hired. So that brings us to our first secret, and we wanted to specifically get into these as this was the label or the title of our talk today. So the first secret is secret number 1 for outreach. And when you're looking for outreach, putting challenges in front of students creates curiosity. And this was a very important thing that we observed. You can go and put that equation, like I said, and you can put it out there, and you can say, spend a lot of time and study this equation, and just believe that someday it will lead to something good. Well, maybe in the past that worked, but I don't know that anybody naturally enjoyed that. In fact, when I was going through school, I remember thinking, wow, I'll have to suffer through this, and that someday maybe I'll be able to do something that would be fun and interesting with it. Well, in fact, what we're finding is that students now who can be challenged on things, it generates a curiosity in them. And this curiosity is a motivation and a drive to actually continue to investigate and work to understand something at its most fundamental levels. So I'd like to give you a little bit of an overview on how this actually can work. So this is a graphic from Dr. David Barrett. Now, Dr. David Barrett is a professor at Olin College, and that's out in Massachusetts. And what they do out there is some very, very interesting things. They, in fact, Dave Barrett comes from a place called Walt Disney World, and you might know that. I think everyone knows this place. But they have a core of technicians and engineers who work there, and they call them Imagineers. Well, he ran the Imagineering department for many years at Walt Disney World. And he decided that he wanted to take all of the interesting things that he could do with technology, and he wanted to be on the education side because that's where our next technicians and scientists and engineers would come from. So he went to Olin College, and what they did there was they decided that they were going to understand what it was that makes a student's brain work. What are the things that they're trying to do? And he said, you know, my job here is to really build the brains of students. And so he said, well, how do you do that? So he began a lot of studies on things like neuroscience, and he talked to a lot of people about how things work. And he found out about reinforcement. And so here's some of the things that he discovered. The first thing he discovered was that students learn, some learn slower than others, some learn faster than others, and there's an average. And there's some range there, but all in all, students will generally learn things as they're presented to them at some positive rate. And so he said, okay, when we take, say, a several-week period or a month period, and we teach students something, if we test them right afterwards, well, then we get some level of the measure of retention. And those numbers, we know they average out maybe 70%, 75%, 80%. And all of us look at that and say, well, that's a good thing. But then what happens is if several weeks go by, or a month goes by, and you ask those same students about the types of things that they learned a month ago, it's almost as if they never ever learned it at all. And in fact, they'll say, no, I never studied that. When in fact, they did, and they retained a little bit of information, but not much. So you see there was a huge uptake, but there was a big decay that occurred, and the net knowledge gain was actually pretty minimal. So he said, how can I interrupt the decay process? How can I interrupt this decay process so that the net knowledge gain is not so low over time? And it goes back to my example about bonding with the equations. What could you do that would actually make an equation so interesting that you would be friends with it, you would trust it, you would know it, and you would definitely remember it? And so what he discovered was that if you can tie in emotional elements to the things that you have learned, you reinforce these neural connections. In other words, you can remember the things and you'll be able to utilize the things that you've learned over time. And so here we show a little picture of an airplane that's nose down in the backfield behind the school. Now, interesting thing about this is that the students worked for maybe weeks and weeks to create this airplane. They put a small controller in it because they were going to try to level this airplane out. And then they were out there flying it. And they got it off the ground, and then when they went to get the up and down right, the thing actually, instead of climbing, nosedived when the automatic controller took over, right into the ground. And pieces flew all over the place. And there was a lot of emotions expressed at that point in time. And the thing about that is that the students now were able to go, and they were extremely curious as to what went wrong since they'd put all this time and effort into building this nice airplane. Well, the answer was that they had the negatives and the positive sign reversed in the equation. And so now you ask the question, is it really important? It was just a sign. Should I get full credit off? I just had the sign reversed. And the answer is, it really matters, especially if it's a mission critical thing like an airplane. So the students were able to bond with the equations of PID and closed loop control and basic things like that. They're able to bond with this, and now they are definitely remembering that. If you test them on it a month later or 2 months later, they're much more likely to remember it, and their ultimate net knowledge gain is much higher. So that brings us to our next secret that we'd like to share. That's for in the areas of retention, that the tools that they use enable experimentation. And if you want to retain students, the experimentation and the testing out and discovery of things is critically important. Now here's the thing. If the tools are so difficult to use that you'd spend all semester trying to figure out how to make the tool work, then you're not going to be able to get into any experimentation. And so one of the important elements of education, especially around technology, is that the tools come in and they make it as straightforward as possible to get off the ground and make something happen. also in those tools, they need to have depth and capability that once the curiosity continues to peak, you're able to dig deeper and deeper and apply the tools to more and more. So the tools will definitely enable experimentation. And if they're able to get the students engaged quickly, then the students will be able to see things for themselves and bond with the theory. So let's talk a little bit about what students are actually building and how some of the tools enable the experimentation. So in fact, when we talk about things these days, we're not talking about just simple products anymore. We would talk about something that we would call a system. And a good example of this is your cell phone. So if you look at your cell phone, some of us can remember the day that the first mobile phones came out, and that was incredible. In fact, I remember back in 1979, I think it was, that one student came in and he had a handheld walkie-talkie. And this it was shortwave, and it could talk to the repeater, and he could make a phone call from inside the school. And we were dumbfounded. We were flabbergasted that this was possible. And he actually made a call, and we all crowded around and said, he was making a call. It sparked our imagination. Wow, could you imagine? You could make a call from anywhere. Today, that's not nearly good enough. That's just fundamental. In fact, our smartphones have to do everything from that, as well as MP3 and video and surfing the internet and texting our friends and keeping in communication. They're amazing systems of communication. And in fact, when technologists go out into the world, they're going to be either using systems or they're going to be building systems. And being able to interact with systems now, like communication systems and transportation systems, we call those cars now, right? Complicated things. But they're systems of components. And so if you are going to build a system then, and understanding the parts, you would then be able to experiment and build systems yourself. So let's take a look at the elements of a system here. The I/O, reaching out and measuring the world, and then reaching out and pushing the world around and seeing how it responds, is a critical part. And this all comes down to basically voltage in and voltage out. And that can turn things like temperatures and pressures and light and strain and all of these things. They need to be turned into voltages, they need to be read into your device, and then you decide what to do, and then you can push that value back out. So that's an important part of a system. The next one is the mathematics and the analysis, and I can tell you, this is critically important. All of the theory, all of the math, all of the application needs to be available, and it needs to be utilized within a system. And you may or may not know it, but some automobiles have at least 20 processors in, and some have as many as 120 processors in them to give you something that we call a ride, right? So very important. All those processors are running algorithms, mathematics, and analysis. Next important part of the system is the user interface. And importantly, computers do not run everything. We have to still interface with them and interpret the results and input things. So having user interface is important. Now on the bottom row here, there's a couple things that are important too. One is that when you create something, you need to be able to run it on something. And for many years we ran it on something called a computer, a desktop computer. We run it on a laptop. And then more recently, there's been a whole wide amount of targets that have come along where you can take a program, put it on a small card, and put it out into the world. And then moving on are the technologies that are used to run inside these targets as well as inside our computers. This is another part of a system. And we might have heard about these things called multi-core. Multi-core has come along, and whether you wanted it to or not, it walked right through your front door, and it's now probably sitting in your house somewhere. It might be dual-core, it might be quad-core, and I have to tell you, octal-core is coming. So all of those technologies. Well, right along with that multi-core processor came something called a field programmable gate array. In fact, that showed up in your house inside of a television, likely inside of a television at first. But now they're becoming widely used because it's like having a piece of silicon integrated circuit chip that you can program on the fly out in the world without having to send it back to the factory. And they're so fast and so capable that now they're becoming a critical part of what technicians are using and what scientists and engineers are using in their systems. And then finally, the last part of a system would be the way you program it. And we call these models of computation, and that means different ways of programming things. And there's ways to programming things with text, but there's also ways of programming things schematically, like a flow chart or flow diagram, and all different ways are being utilized. So those are the elements of a system. Now, if you take those and you can combine those and be sure they'll connect together, then you're going to be able to experiment very quickly. And this is what's important about getting students up to speed. So if you had to program all of this with things like text code, that's probably going to take you the semester, and that's not going to enable the experimentation. But if you can be sure that all of the things that you need to do, like the input and the output, the mathematics, the commercial technologies, the user interface, and the different ways of doing programming are all compatible, then you've taken a big step forward of not having to spend all semester to hunt down the compatible elements. So that's one step. The second step is, if you can be sure that all of those elements can communicate to one another, and what we say is they can integrate together, then you've taken another huge step forward at being able to make sure you can get the things to work and be sure that they can communicate to one another to create the thing that you'd like to experiment with. Well, if you can understand this, National Instruments makes a product called LabVIEW, and LabVIEW, if you look at this next slide, is exactly that. It's the combination of these elements and these pieces inside an environment that ensures that they'll be able to work together and guarantees that you can communicate back and forth from one to another. Now, this can be done very rapidly, and you can make whole programs like the one that you're seeing on the screen. And that's what's allowing educators, from our perspective, to get students up and experimenting very quickly so that we're retaining their interest and we're getting them to bond with the theory that is so critically important and demonstratively relevant to the things that they're doing. So when I talk about National Instruments, then, I'm talking about a company who has a large platform that spans all the way from circuits and electronics and RF and controls to the hardware that we can put in the hands of educators and students. And we've worked hard to bring those prices down, and we glue all of these together with that piece of software I just showed you called LabVIEW. So that's a little bit of a background of where National Instruments fits into the bigger picture. So that brings me to my third secret. And when you want to graduate students, it's important that they're able to go out and demonstrate to prospective employers that the things that they learn are both relevant and they're able to demonstrate that the things that they do are viable to actually work in the real world. So the viability is real important. And in fact, experimentation shows you this all the time. So I'd like to walk you through a few of the things that demonstrate this. We start with this guy, Thomas Edison, who is one of the most famous inventors that the world has ever known. And you must admit, Thomas Edison's track record was very good. He kept a notebook of ideas, and he labeled it things doing and to be done. He wrote down things like light bulbs and batteries and phonographs and electric pianos, all of these things that he brought to fruition, and he wrote them down before he ever did them. And it was incredible that he had the courage to actually say he was going to do those things and deliver on them. And then, of course, you know, the light bulb was a huge thing. But the real question is, how did he do it? How did he know that he was going to be able to produce viable things? And, you know, and the world was his employer, right? So when he went out to the world, he was going to produce things that he knew would work. Well, how did he know they were all going to work? And here's the answer. This is his Menlo Park laboratory, where he searched high and low, far and wide, to get all of the pieces that he would need so that he could walk into this laboratory any moment that inspiration struck him, put the pieces together, and say, I'm going to try it 100 different times, and the 101st time is going to prove viability to me, and I'm going to be ready to participate in changing the world. And his laboratory was an incredible, incredible way for him to do that. So how do we do engineering now, though? How do things actually happen at this point in time? And in fact, what happens now is students and educators can go to their Menlo Park laboratory. It's something that we call the Internet. The Internet is this incredible repository of all the world's offerings for the things that you could get your hands on to experiment with, that you could retain your curiosity with, and that you could prove viability. And importantly, once you do that, once you have done that as a student, every little experience that you gain that proves that you know something is possible and it could work and that the theory is actually relevant becomes a line item on your resume to prove your value to a prospective employer moving forward. Now at National Instruments, since we're so hands-on and we're making the technologies and the tools that we've used with technicians and scientists and engineers around the world so many times, we call that do engineering. We talk about not just simulating it, not just theorizing about it, but actually experiencing it in a way that we couldn't think of two better words to put together than to say, you will do engineering, therefore you will know engineering. And from a student's perspective, you will be able to participate. So at that point, I think we have a question break, and I'd like to stop and take any questions that people might have at this point.
Thanks, Dave. Very interesting perspective on tying these things together. You know, one of the comments that appeared in the chat window, and by the way, I invite everyone to put either their comments or questions right in the chat window, and we'll get to them as time allows. But as you know, Dave and Mark, retention, well, it's not only at universities, but at community colleges, retention is a big issue, and so we're always thinking, you know, what are the things that will actually help and that have demonstrated effect on retention. I think you're hitting at them here. You referred to it as bonding with the equations, or a term that someone asked about, emotional reinforcement. Dave, do you think that's the same as like experiential, or is there another component there that causes you to call it emotional? I'm very curious myself, in addition to our one of our colleagues online asking that question.
Yes, so that's a great question, and I think the experience is critically important because once you've experienced it, then you sort of know. If you've done it before over and over again and somebody tells you different, you say, well, you can't prove that by me. I've done it this way so many times. I know this works. I know that didn't work. And so the experience gives you that fundamental backing to actually say, I believe if you do this, it's going to work and it's the best way. And that's valuable. That's very valuable. But the real question is, what motivated you to persist long enough and probe into the things so much that you were able to invest enough time to gain that experience? And that's sort of the emotional part. When that plane didn't fly, I mean, it was fun to build a plane, and it was very emotional to crash it into pieces, and now you have this such strong desire, maybe known as curiosity, but you have this strong desire to know what happened. And so the emotional piece reinforces the pursuit of the experience in a way that once you get it, you will not forget. And then think of your value to anyone when you come out and say, look, we could spend a whole bunch of money doing that, but I've broken 100 airplanes. If you do that, you'll break the 101st airplane. Let's not do that. Let's do this. Now your value to an organization, because you had the motivation to pursue a reinforcing and a confident experience, is critically important.
And you're making a very interesting point there. It isn't just the experience itself, but I guess it's that coupling with the emotional component that really is the reinforcer here. That's fascinating. Makes a lot of sense. I've got a critical question for you, Dave. Did that bicycle ever ultimately work after you finished bonding with it?
So that's an awesome question. And I'll lead up to the answer.
Okay.
I'll have to tell you. While I was on the bike and I'm surging fast and slow on this thing, I'm heading toward the intersection. And like, I don't know what's coming in that intersection, and all kinds of things are flashing through my head. First of all, how am I going to explain this to my wife? Secondly, is my insurance policy paid up? Thirdly, why did I overtune the integral constant? All those are flashing through my head. And the fourth thing was, oh yes, I put an e-stop on the bike that was attached right to the battery, interrupting the battery and the motor. So we were able to tune it, and let me tell you something, it worked beautifully. The thing I think I was most proud of on that bike is that I went to the local store and it was a $100 bike. The bicycle was the least expensive component in the whole thing. We had a $50 motor on it, maybe $30 worth of batteries on it, the controller, and I have to tell you something, it worked beautifully. It worked incredibly well. We actually linked it into the gears, and it was I think it was like a 12-speed, but we could shift the gears in the back and have different gear ratios, and the cruise control worked, and it worked beautifully. And I'll tell you, it wasn't for the faint of heart. There was some metal we had to cut in there, and we were drilling holes and stuff, but at the end of the day, it worked. It worked great.
It sounds actually very cool. I can hear some of the emotional bonding in there in your description of it. I'll tell you what, there's another question about FPGAs, but I think I'm going to hold that till we get to our second question period. Dave, why don't you go ahead? We're timing's really good so far. Why don't you go ahead and take us forward?
All right. Well, thank you. Thank you for those wonderful questions. We're going to move forward, and I'm going to start giving some examples of the tools that we provide and the ways that they're being used so that students can begin to gain those hands-on experiences, the types of things that they were so interested in when they came to school, give them a chance to experience things. And we'd like to spark your imagination that they're not completely abstract. These are hands-on, and in some of the cases, some of the things that we'll show you moving forward are very authentic experiences that we're just very inspired that we can actually bring this degree of authenticity to students. So we'll start with the laboratory, and this is where, of course, students spend a fair amount of time that they're coming in, they're working in the lab. So inside the laboratory, we have something called ELVIS, and we've made a product that allows the consolidation of fundamental measurement technologies. So it provides the ability to put oscilloscope, function generator, power supplies, digital in, digital out, all of that capability inside of one box. And as well as something that's little lesser known but very important, something called data acquisition. Now this is a technology that facilitates the continuous input and output of signals simultaneously. And if you're running a system out in the world, the necessity to be able to continuously stimulate this thing and then read the response back without missing any data is important. And that's a hallmark of a technology that we make, something called data acquisition, and it gives this concurrent and bidirectional signals in and out to the world that lets you do this. Now another thing that we add on top of this is a piece of software called Multisim. And Multisim, if you're sitting in the laboratory, will let you sit there and actually draw up the circuit. Now this is nice because first of all, you need to go out and see that these symbols that are resistors and capacitors, that you can actually recognize these things. But then importantly, you can lay these down on top of a canvas, and then you can connect them together. Now you're connecting the symbols together, and then you push the run button, and then guess what? The software runs basically a virtual electrical current through these circuits, and it simulates what that result would be and what that circuit would do and how it would behave. So kind of interestingly here, you don't have to actually burn up components. You can put them on there, and then you can put these things called virtual instruments, which is an oscilloscope or a voltmeter. You can attach it there and see what the output would actually be. So this is kind of a nice thing. Now importantly, once you make something that you've actually created and run it in a simulation mode in software, then you can build that circuit in hardware. Now the picture you see on the right is that same ELVIS breadboard, but you can put a circuit on top of that thing, and then you can compare how the real world measurement will compare to the simulated value. That's exactly right. So this is what ELVIS looks like, and as I mentioned, this is the piece of hardware. And in fact, as I remember my tools here, I think we have some pointers and different things. Right, here's my pointer. So this is what ELVIS looks like, and in fact, here's a breadboard area, so the students can build their circuits here. But importantly, built into this thing is an oscilloscope. And what's kind of nice from an educational perspective, because ELVIS consolidates all of these pieces, you don't have to go hunting for different parts that somebody may have borrowed. It's all in the box. And so now there's the 100 megasample per second oscilloscope. Here's the waveform generator over here. There's a power supply built inside. You connect to it to a computer that shows you the traces on the screen through USB. And then there's some knobs that you can turn to adjust the power supplies and the frequency of the function generators out. So this consolidates a whole bench top of equipment into a single box, and you always know where all those components are because they're in the box. And then another thing that we did with ELVIS is we made it so that the board on top can be removed, and you can put other boards on top of that. So this will allow you then to do circuits, but then also you can adapt this instrumentation platform to biomedical applications, to RF and communications capabilities, to digital electronics, even embedded and controls can go on here. And there's many different things that we're doing along those lines. So what we'd like to do at this point is show you what some of this looks like. And at this point, Mark, I think we're ready to do a demonstration. So I'm going to turn it over to my colleague, Mark Walters, and he's going to walk us through some of this.
Before we come to the demonstration, I like to show you how we can do engineering in circuits. So here's an example of a DC power supply. And the DC power supply has 4 different stages. Now, as a student, you might learn of these 4 different stages in multiple courses throughout the course curriculum in the circuits and electronics area. The first part is to have your AC input. Next, it's going to be converted or down converted to something, let's say 12 volts, rectified, changed to a DC signal, and then filtered and then regulated before it gets to your electronic device that needs to be powered. So what we want to be able to do is take a look at these different stages and better understand how we can match the theory with our simulations and then do the actual real-world prototype. Now this example is being referenced from a textbook called Circuits that was developed in conjunction with NTS Press to really highlight circuits, examples, and curricula with modern real-world examples to help students be able to make that connection with the theory and the actual application. So Mike, if I could ask for your help to pull open the first video.
Yes, I'm happy to do that, Mark. For those of you in the audience, this is sort of a unique experience for us today because we're going to be running a video with a live voiceover. And when the video comes up on your screen, it should launch automatically. But if it doesn't, if there's a play button right in the middle of that video screen, it's just a normal YouTube screen, hit the play button. So here we go, Mark. I'm going to get ready to launch the video, and then you just go ahead and do the voiceover for us.
Great.
Okay,
Thanks,
so
Mike.
I'm getting ready to launch. Here we go.
So as we get started, if it hasn't started for you already, go ahead and hit the play button on the lower left-hand corner of the video window. What we're looking at right now is the ELVIS laboratory platform. What I'm going to go ahead and do is turn on the platform, make sure that it's connected up to my PC, and you notice that it's set up and ready to go when those lights come on. Now I'm going to switch over to our Multisim environment. And one thing that I want to be able to point out is these rails. Now these rails mimic the same configuration of our ELVIS breadboard. So it has our pinouts for each of those inputs, let's say our function generator or our oscilloscope, that allows the student to be able to make the configurations and connect them up to the right pins, getting them closer from the simulated world to the actual prototype. So I'm going to first drop down a resistor onto my circuit schematic and then have that understanding of that circuit to be able to connect it up to my input signal, which is going to be my function generator. Now the unique thing about Multisim is it's developed for education, so there's pedagogical features that really help the student better understand the equations themselves to get a deeper understanding of the material. One of those features is a 3V breadboard. One of the big challenges that we find in a circuits class is being able to convert from the equations to the circuit schematic, but then taking that next step in order to be prepared in order to build up the circuit. This 3D breadboard helps that student be able to go from that circuit schematic and then build in the circuit into a virtual environment. Let's say this is a pre-lab assignment in their homework, to start practicing breadboarding before they actually get into the lab. Understanding that that lab time is very, very valuable, and we want to make sure we're able to maximize it to achieve all of the different concepts that we need them to cover. So I'm dropping down that same circuit that I had on my schematic, and I'm going to go ahead and practice wiring up that circuit on the breadboard to make sure that I have it hooked up and connected correctly. Once I have it dropped down, one of the things that I can do is do a check with my circuit schematic. And you'll notice that my circuit component turned from black into green, meaning I've correctly placed that circuit onto my 3D breadboard. So a student can go through these different steps in a very safe environment, sometimes in their own home on their own laptop, to try to get that better understanding and prototype and work through these different exercises before they go into the lab itself. So what I like to do is kind of step through an example that we just worked through, which is going to be our digital power supply. Now this is actually going to be the circuit of our bridge rectifier. So this is going to be converting 120 volts using a transformer to break it down to 12 volts, and then converting that AC signal into a DC signal. So we've built out our circuit similar to what we saw in our circuit schematic. And now what we like to be able to do is test out and make sure that everything's hooked up and connected correctly. And this will make sure that when we run our simulation, we'll be able to get the deep understanding of the material and get a very good understanding of what the relationships are with the equations, with our input signals and our output signals, with our diodes and our resistors, to make sure that it's set up correctly as expected with the right values and we get the right output. So once we have it set up correctly, what we're going to go ahead and do is open up our oscilloscope. So this is going to be a virtual oscilloscope that's going to be run on our computer. And this is going to allow us to be able to measure the output of our bridge rectifier circuit. So I'm going to make sure that it's set to simulate. Another option is to actually hook it up to the hardware, which we'll do in just a second. Now I'm going to be measuring the output of that bridge rectifier, and I'm going to go ahead and hit start so we can start seeing the signals that are going to be coming out of our 120 volt AC signal. And now we have our measured rectifier circuit, and we can actually confirm the correct behavior, the correct components, and the right sequence of steps to confirm that the simulation is working as we expect, exactly as we saw in our textbook and our lab materials. The next step is to actually build out this circuit. So we have our DC power supply built up on ELVIS. The first step is going to be our bridge rectifier, then our smoothing filter, and then our 5 volts regulator or power supply. We're going to go ahead and start taking a look at the bridge rectifier part on the second stage of the DC circuit. What we want to be able to do now is go back into our software environment and change from the simulated signal to our actual physical device. So now we're actually doing the real live signal from our ELVIS board. And we're going to go ahead and hit and start up the circuit so we can actually see the measured values as opposed to those virtual values, and see what the comparison is between the virtual signals and now our real-world measured signals. I'm going to go ahead and make sure that I have it set up and connected to the right pin. And hit start. And now we can measure the actual signals that are coming from the ELVIS device. And you'll notice that there's a little bit of an offset that we're noticing. A lot of this is from some of the noise that might be introduced into the system, but also some of the parasitics as part of the components, which is a very good understanding of sometimes that real virtual signal that you simulate doesn't quite exactly match up exactly in the virtual world, in the real world, as you might expect. This gives the opportunity for somebody to really get a deeper understanding and make some adjustments based off of what that output signal is really going to require. So this is just one example of how you're able to go from the theory and the equations and go to an application to really understand the different steps that are required and get a deeper understanding from that equation level into the simulation and the perfect world up into the real world and actually build out the different circuit components. And the integration between the theory and the textbooks, the course material, the software simulations, and the hardware allows that student to really focus in on the material and spend more time gaining that deeper understanding of the theory and the concepts so that they can be better prepared to answer these questions when they go into the lab and complete the real-world prototype of these examples.
That looks really good, Mark. I like the way you're actually able to demonstrate that live, sort of, right here on the screen for us. I'm going to jump us back into the presentation now. There we go. So Mark, it's right back to you. I know you have 2 more shorter demos coming up, so go ahead and take us forward.
So the next thing that we would like to talk about briefly is we recognized, and this is Dave, by the way, we recognized that the students more and more had the capabilities with their computers and their tablets and their phones to do things in places other than the laboratory. And in fact, if we could combine that curiosity and the motivation to understand things and allow them to access, at the moment that they were curious about it, access the instrumentation, that we would actually have a very good approach to letting them learn about these technologies at the time that they were interested and motivated to do so. So we created something called myDAQ, myDAQ, and this device is as says, designed to expose students to this hands-on and project-based learning. And it is a device that you can sort of think of as the small version of ELVIS. It's something that runs off of USB that they can plug into their laptop. It's got analog input capabilities and analog output capabilities, so it can read waveforms in and out at 200,000 samples per second on each channel at very high resolution. They can detect 300 microvolt changes on these channels over plus and minus 10 volt ranges, so very, very nice instrumentation. Analog in, analog out, digital in and digital out. It's got an isolated voltmeter on it and can also read audio in and audio out. So this was a device that we put together that would allow students to go and do engineering anywhere that they wanted to. And in fact, many things that have come along with this, and I'd spoken about the authenticity, the types of things that you could actually run, not just simulate, but run. And we've got a whole ecosystem that's beginning to develop up so that students could go and put a power grid into a device like this that wasn't just a simulation, but something that would actually generate power, AC signals, step them up, step them down. They would be loaded by lights. You can see some small houses up there that turn on and load the grid down. And there's a supplemental power source for DC when the solar comes out so that you can actually see how the grid would fluctuate. Then you'd have parameters. And instead of just going on a field trip and walking around and looking at the big transformers, you'll be sitting at the helm of a real power plant seeing how it behaves and it works. There's a small helicopter there for vertical takeoff and landing, and then there's a small dynamometer in the lower left-hand corner so that you could actually run this thing and be able to see how the power output of a battery or a motor would actually function. So what we would like to do is jump back into another demonstration and show you how this would work. And I'm going to turn it back over to Mark. And this is going to take us through more of a biomedical application because I think that's an area that many students would be interested in.
Great. Thanks, Dave. So the challenge is to actually be able to do something, build something, a student project that a student can relate to. So Mike, I would ask your help to pull open the next video incorporating myDAQ.
Okay, Mark, I'll just remind folks that if when it comes up, if they need to hit a play button to go ahead, but I think for most of us it's working fine. So I'm going to go ahead and launch it now. Mark, its floor is yours.
Great, thank you. So the challenge is to actually create something that you could measure the heart rate in a person. So in order to do that, whenever your heart beats or pumps, it's going to send out blood through all of the extremities. Now there's a relationship with that heart rate where you can actually take a measurement using an LED and a photoresistor in order to measure how much of the beat is actually happening. So we're going to be using a myDAQ unit that you see in front of me. And I'm going to hook up a small little device that I created on a PCB that includes a photoresistor and an LED inside of that black little terminal, and I'm going to use a photo voltage divider in order to measure the resistance that's coming through. So as I shine that LED on my finger, I'll be able to measure each of the different heartbeats. And I'm going to be using LabVIEW in order to take that measurement. So as I get started, I'm going to go and do a little bit of a calibration to make sure I got the right signal. And then you can notice each of those peaks is going to be representative of a pulse. Now that red line, you'll notice that the signal is not as clean as you might see at a hospital. But what that red line allows us to do a little bit of signal processing so we can measure that peak detection and then use a threshold using some signal processing in LabVIEW. So we're able to measure and take that measurement. What I want to be able to do now is just pass over to our block diagram so I can explain how we developed this program. So the first block is going to be acquiring our signal, so taking that voltage measurement across our voltage divider. The second one is going to be taking the peak detection and then taking that and measuring the amplitude and converting that to our beats per minute. Finally, we're going to go ahead and show you that threshold, which is represented with that red line. So using parts that cost about $2 to $3, we're able to create a very low-cost project, incorporate that into myDAQ, and offer the student the opportunity to create an open-ended design problem in order to solve that application. Great. Thank you, Mike.
Excellent, Mark. That worked really well. I'm going to take us back to the presentation now, and you and Dave go ahead.
So as a quick summary on this device that Mark created with the LED and the photoresistor, that's called a plethysmograph. So it's got a big fancy name. But the amazing thing is when you think about it, the student can take that, and I tell you, when I did this the first time, I thought, wow, like everything's working. There's actually blood pumping through the tips of my fingers that is measurable. That's incredible. And then you're faced with the fact that how do you actually do the signal processing to get a good steady reading? And that's a challenge. And now the mathematics swoops in to rescue you to actually figure out how to make that a steady thing, so that when you make yours in the future and you sell this as a product, that hospitals would have a good, nice instrument. But this is the seeds of that and the very fundamentals. So the next thing that we said was, this is great. Now students can actually do those measurements. They can do them in their dorm room or in the coffee shop. But we said, you know, the next thing we'd like to be able to do is have it a box that you could write a LabVIEW program, that you could put that LabVIEW program with all of the programming capabilities, all of the math and the analysis that you might want to do, vision capabilities, be able to make this communicate and connect through RF. We wanted to be able to put that in a box that a student could carry around, something that was just a little larger than a cell phone, in the exact same size as myDAQ. So we went and we developed a device called myRIO. And RIO stands for Reconfigurable Input Output. And I'd love to spend about an hour giving you all the details of this thing, but I'll just give you a quick overview of it. This thing is running a processor that you can take a LabVIEW block diagram like the ones Mark has been showing you, and instead of running it on your laptop, from your laptop you can target this device over USB, and you can put the program down in there and you can run it. And this is a powerhouse of technology inside of this thing. We like to tell you that there's 92 billion calculations in your backpack, and that's what the student can run on this thing. It's what they call a Zinc chip, and it's got an ARM dual-core processor on it. It also has that FPGA that I mentioned. It's in there as well, and these things run what we like to say deterministically, meaning that if the loop is supposed to take 10 milliseconds to run, it takes 10 milliseconds to run every single time. Unlike Windows, which might be a couple milliseconds and then 20 milliseconds, this gives you the certainty that it runs and it iterates at the right rates every single time. Now, there's other things. It's got a lot of input and output, over 50 channels of analog in, analog out, digital I/O, as well as the ability to communicate through some of these buses for communication, like the serial buses, things called UART and I2C, as well as pulse width modulation, encoders, and so on. So it goes on and on. But this box has a lot of I/O. It's got real-time capabilities. It's programmed pretty simply with LabVIEW. And it's DC powered, so you can go and put this out in the greenhouse, on the wind turbine, on the electric bike if you so desire to build one of those. And we put this together. So this is something that we announced in August of this year because we wanted to give the students the ability to access all that relevant mathematics and analysis, but then we wanted them to be able to go put that on their projects and run it as quickly as possible. So at this point, we're going to switch over to, I think, our final demonstration, which I think is going to bring to bear this authenticity I talked about, but you'll also see this embedded program running. So, Mike, if we could get you to bring up our third video. So here we go. This is myRIO, and I've described this. One of the things I didn't mention is also in here is that it's wireless. So once this finally gets running, you can walk up to this with your iPad and you can run it. Here's the connectors for audio in and out, as well as the I/O I talked about. And then a lot of that I/O is replicated and extended on this side for over 50 points. You connect to it through USB. You can hook a USB camera into this if you want. You DC power this. And at this point, Mark is hooking this all up. So he just powered it up. It's booting. He's plugging the USB in, and you'd only have to plug that USB in if you wanted to change the program. So he could load a new program into it if he wanted. Then he could unplug that USB, and we could have this thing running completely autonomously. Now what's happening as it's powering up, it's actually booting it's booted the device itself, so it's up and running. And then inside the device lives the program, and it's running automatically at startup. Now down here in the bottom right hand corner are a couple small buttons, and that button connects to the wireless. This actually starts it. This is running a small plant called a continuously variable transmission. You might have seen these cars have these, snowmobiles have these, and these are two cones, and they're different ratios on each side. He's pushing the button, and we have a servo that's in this little device that's moving the belt and positioning it to different points on these, and it's actually changing the speed. Now when he loads this down, he actually stalled it out there, which is kind of a cool thing because that would really happen if you shifted too fast in your car, you let the clutch out too fast. But you can see it's auto shifting. When he loads it down like he's going up a hill, it shifts into low gear, and then when it's not loaded anymore, it shifts up. And then he clicks it again, and he puts it in park. So you can see that there is many things that can be done. This is a small little plant. It's a prototype that we put together, but it shows these types of things that students could now actually go and see, not a picture of a transmission, but they could see how it works. And then you could have a front panel that would let you operate this, or if you were the student that actually wanted to build something complex, you could come into LabVIEW and you could program it. So we'll show you when that was sweeping back and forth to the different gears. It was a little program that is running in LabVIEW that's been loaded inside of this box. And so here's the front panel. You can do the calibration for the arm offset. And if we go back into the diagram, here are the functions that say read the load, how much voltage is coming off that motor. I want you to sweep a sine wave and then go move that servo arm position to change the gears so that you can sweep back and forth in a sinusoidal fashion. So this is the whole program that would actually get that done. Now inside any one of these functions you can go in and you'll see settings inside of a function that you could go and you could change, and you could actually set parameters inside of any one of these things. But what Mark and I liked when we saw this, when we were doing this ourselves, from the biology standpoint of actually measuring a heart rate, to going and experiencing the different gear ratios and setting different gears to get more power or more speed depending on what conditions required, that a student now could sit at their desk and could experience this, and in fact they could do engineering, they could do their technician work, and they could understand not purely from a theory and simulation standpoint, but by seeing the effects of this. And one last point, when we were actually running this, we said, oh, you know, if you let the clutch out too fast and you shift gears too fast, you have to actually increase the power or that belt will grab. Well, we wouldn't have thought to put that into a model for simulation. But I can tell you when the real physical thing happened, we knew it was something that was real and out in the real world. So we were able to bring authenticity and interest in real challenge to solve a problem. Now you could actually go and say, yes, you know, I'm applying for a job at this transmission plant. I've actually run transmissions. I have a feel for the fundamentals because I've experienced them. So we'll quickly walk through just a couple pieces, and then we're happy to take any questions. We'd like to just make some comments and show some observations in different fields where this concept of experience in doing technology, doing engineering, can actually be used. So on the outreach side, if you're looking at power and energy, our partners at Elenco make a small power grid that I described to you already. But here's two students that were actually sitting there running, and they'd cover this up, and the sun would come out, and they would see how well they were optimizing the output of that little fossil fuel plant there. And this wasn't a simulation. This was now the lights were coming on, and they were trying to see if they could tune this thing so that they would save energy and produce the best results. In the laboratory, this is a lab that was put together by a partner of ours called Emona, and they add on top of the ELVIS instrumentation platform many of the things that students could go in to experience how solar output actually works. A hydrogen fuel cell, and I really like this because everybody talks about fuel cells. Now you're actually going to see a hydrogen fuel cell in action, and you can get an intuitive understanding of how fuel cells work for the space and the density they have versus how a solar panel would work in the laboratory. And then here's one testing the durability of a wind turbine. When you get out in the real world, you will take your RIO-powered platform that you've actually had experience with in the college and go onto the wind turbine and measure things like frequencies and power outputs because you've had some experience in that world. Moving quickly into controls and mechatronics, this is a whole world that's very exciting these days, and starting at the most fundamentals. So I like to talk about the electric bike, but the more common use of cruise control is with the car. And here's a prototype. This is a small dynamometer, and the car runs. You dynamically load it down, and you're able to measure the power capacity of a battery or how much this car is able to output for any given throttle setting and any given load. And then when you walk into your prospective employer, you're able to say, yes, I've actually played with these things. I have a good fundamentals. Let me show you what I've done. And I think that experience is far beyond what many students would be able to do without this type of technology. Here's one that's a very exciting one for something that for advanced controls. But if on your resume you can say, look, I work with the equations for an inverted pendulum, that just means that you know how to do something that people can understand and appreciate at a controls level. And in fact, if you've ever seen a Segway run, the basic equation set to get the Segway to stand up is the same thing that they would have, and they would get experience here right on the bench top. Here is controls being deployed out in the world, and once again, we talk about the emotional connection of technologies. This was a university, actually at Virginia Tech, that went out and took the controls and the feedback and allowed blind drivers to drive vehicles for the first time in their lives. And for these students, it was a way to say, yes, technology matters. The equations are critically important. This was mission critical, and we were able to go and experience something that made a difference and was highly motivational. On the communication side, let me quickly mention, on the outreach point, this has been a real exciting one for us because all students listen to music in some form, and the devices we make allow audio signals to come in. The question is, how do you modify these signals and see a difference? Well, we've all seen treble, bass, the tone settings for music. The question is, what are filters really good for? Well, they're good for exactly setting that treble, bass, and tone. And so this right here allows that to be implemented. You can see the three icons stacked on top of one another are the things that actually go and set that tone. We had a couple students take this a little bit further when they discovered that the left channel and the right channel have one signal that's common to both sides, which is usually the lead singer's voice. So they subtracted the two signals, that canceled out, they put the leftover back together and pumped it out and created their very own karaoke machine, and they were able to extend beyond the most fundamentals and see that they could create something that they imagined. From telecommunications, the fundamentals and the bench top, this is ELVIS, and connecting the pieces together, they're able to route signals and see how signals are transmitted or possibly degrade depending on the ways that you pass them through. And then finally, what we're finding now, and this has been very exciting for us, we could talk for an hour about this, but this is taking technology where only in the past would you ever be able to read about this, but now you're taking and you're able to down convert signals out of the air that are RF radio signals. You can down convert them, you can demodulate them, you can reconstruct them, you can put them back together, and you can rebroadcast. In fact, when this first came out, I was able to actually create my first FM radio, and I was very proud because it was only about 4 functions. I took the derivative, I was able to actually see the result, and I said, hey, I can actually hear the audio baseband and hear what that sounded like. And about 2 weeks later, 4 students sent me their accomplishment with this device called USRP, which was a television digital broadcast station, and I realized that the students, once given the technologies, could go way beyond my FM radio capability. So it was really inspiring to see how they were able to run with this. So in our talk, we were trying to go through the things that inspire students and connect with their desire to experiment, and then bring them into colleges and universities where we could retain their interest and retain their participation by showing that these technologies are available and they could see that it was relevant and important and applied to things that were interesting and mattered to them, to the point where they could prove out, gain experiences, and be able to actually have opinions for contribution on the viability of the techniques that they had learned and actually put together. So at this point, I'll turn it over. I'll let Mark have a few final words, and then we'll take any questions that you might have.
So we're interested to hear from you and see how we can partner together. For more information about some of the tools and solutions that you heard from us, you can request an NI consultation. So working with one of our NI engineers to learn how to incorporate some types of solutions into your course. There's a 3-part webcast series that's targeted and focused on circuits and electronics, talking about the latest trends, some of the best practices from educators, and then a couple of solutions in order to maximize the time inside of your classroom and inside of your lab. And then finally, all of the teaching solutions and training materials you can find on ni.com/academic. And with that, we'd like to encourage you to work with us in order to do engineering inside of your courses and at your university as partners to prepare students to be ready for graduation and be prepared for their next careers in industry and in advanced research.
Thank you, Mark. And Dave, you know, it's really a great message that you just stated there, because ultimately we deal with this issue, right? We have students in our programs, no matter where we are in the country or in the world, and we want to encourage them to get the credentials they need. That could be a 1-year certificate, it could be a 2-year degree, a 4-year degree. You know, that's where we want to get them, so they have credentials that they can take into the workplace. Dave, let me remind folks to put any final questions they have there. I was really struck, and several people online were commenting as well, how about you saying, you know, you can take this into a job interview. And I think you're right about that. I think you could go into a job interview, I'm a student now, say, yep, I know about these control systems, as you mentioned, the inverted pendulum or the CVT. And that allows an interviewer to actually see that the student has that direct knowledge, not some textbook knowledge, but they'll be easy to tell in that interview. And boy, I think that makes a difference. I don't know if you want to comment a bit further on that.
Yeah, I would love to. That's exactly right. It starts with an element. You said credentials. That's the perfect word. They've got some credibility. They've got some things that they've done. But here's kind of where we're excited. Some of the things that the students are doing, understand they're doing this with tools. These tools are new. They're state-of-the-art. They're fantastic performance. They're able to implement the mathematics standalone, ready to run. And so the exciting thing for me is the student can walk in and not only say that I've actually been involved and I understand how this works, but I'm actually coming to you with knowledge. where I can actually bring in and deploy these new techniques that can improve things, and I will make this place better for me walking through the door. So they actually bring in a very contributory way when they walk in the door the capabilities that go beyond just that I understand it, but I can actually bring you improvement by you hiring.
That's a really good point. Before we go to our final question, Dave and Mark, I want to ask the audience to help me pay the bill. I know that sounds funny, but I'm going to launch a very brief survey right in the middle of the tail of our webinar here, and that will mean you'll be able to respond to the questions. There's only 5 of them, and it only takes, it should take you less than 90 seconds to do this survey. So Mark and Dave, don't touch the survey while it's up there so we don't accidentally close it. And audience, just go ahead and click on those radio buttons, and if you have a moment, respond to the text boxes as well. So that's our survey. That helps demonstrate our value and our impact to the National Science Foundation, who helps fund this series. Dave and Mark, another interesting thing came up. You mentioned FPGAs, field programmable, excuse me, I'm tripping over it, field programmable gate arrays. You mentioned that several times. Now, I know community college programs across the country are more and more incorporating that technology in. Do you view that as a good thing, or let me phrase it slightly differently? Where in a student's course of study should they first start learning about FPGAs? Do you think that's a second-year topic, or where have you seen that incorporated? Where have you seen that first introduced?
Well, that's a great question. So I could see it historically. The difficulty in programming FPGAs would have probably relegated it toward mid to later years, because you'd have to know a lot about programming. You'd have to be able to get very down and detailed to make it function. And so they were sort of not for the faint of heart. And so there were a bunch of tools that came along to utilize the capability of FPGAs. So one of the first that we did was Multisim. So Multisim, you'd actually be able to go and create digital logic in what you say this diagram or panel in Multisim, and then you target an FPGA and it would go off and do that. So that was giving you a little bit of earlier access to it, but not necessarily getting down and programming the FPGA. One of the things that we did at National Instruments was we took the block diagram methodology, or we call it data flow, but this is programming in LabVIEW. And we said, you know what, if you can describe functionality in a LabVIEW diagram, we're going to be able to reach out and target the FPGA to carry out that functionality. So what started happening is if you could think schematically and express it as such in LabVIEW, then you could hit a button and it would compile it and turn it into the VHDL code that would run on the FPGA. So what happened there was sort of a drawing into earlier years, the ability to go and experience this. And with the incredible processing speeds and determinism and reliability of FPGAs, now I think having a way to be able to program this without studying 2 or 3 semesters on the deep details of very, very meticulous programming, instead you can express the functionality and you can burn that chip, you can burn that FPGA right there and have it ready to go. And if you get it a little wrong, you can reburn it, which is great, but you can iterate on that to the point where when you go to deploy it, you're going to be able to make it do some very, very sophisticated things. So long story short is that things like LabVIEW make programming those much, much easier, much greater access, so it can be done earlier and earlier in the education.
That's a good point. And speaking with our own local industry folks here in Phoenix, Arizona, they're increasingly looking for FPGA skills and abilities in both technicians and engineers. So I was pleased to see that. Folks online, I'm going to close this survey now. Hopefully somebody isn't right in the middle of a long essay into one of the text boxes. So I'll give you a countdown. Please submit your survey. I'm going to count down to 5 seconds. So submit your survey. 5, 4, 3, 2, 1. Okay, that's closed. And thank you very much for doing that. Dave and Mark, let me just wrap up here as we get to our conclusion. Today, you can, well, it'll take an hour or so to post this, but you'll be able to access the recording, slides, and handout by going to our website, maytechnetworks.org. and just typing in Top Educators Secrets. You'll see lots of other archived webinars there as well. Here's one that's coming up just later this month, only a couple of weeks from now, mechatronics, a very interesting field that has a real emergence in the past 18 months or so. You can register for that webinar at myDAQnetworks.org as well. By the way, if you'd like a certificate of participation saying you attended this live version of the webinar, Janet at janet.pinhorn, that's her email there, she can send you one. She's going to look at the attendance list to make sure you're actually here before she sends it to you. Little joke there. Join us in Chicago this summer, July 21 through 24, the High Tech Conference, that's High Impact Technology Exchange Conference. About 600 people whose vital interest is right what we've been talking about today. You'll find people who really live the sort of things we're talking about today, how to use technology and engage students in technology to help their retention and persistence all the way to completion. So join us into High Tech. Take a look at the website, highimpacttech.org. So those are the commercials. Thank you for attending today's webinar, Top Educators Secrets. You know, Mark and Dave, as I was thinking about what you were saying, sure, I know there was some technology-specific things, but this idea of engaging students both emotionally and experientially, that's got to cross disciplines, whether it's biotech or IT or mechatronics. I think some of the things that you had to say today, many of the things, all of the things you had to say today really resonated with that, so I wanted to thank you. Any closing comments from you, Dave?
It was really our pleasure. Thank you for the opportunity to speak to people. You know where to reach us. We're National Instruments, and myDAQ.com is one way to get a hold of us as well. We'd like to thank you for the opportunity, and we look forward to working with you and participating with myDAQ in the future.
Thanks, Dave. And Mark, last word to you. I loved the demos. I just watched, I was fascinated with your voiceover and working the controls. It just really worked today.
Thank you for all your help putting this together, Mike. It's been a pleasure, and we want to thank everybody who joined us today.
Everybody online, this officially ends our webinar. When I turn this off, Mark and Dave, you'll be gone, so I won't have a chance to talk to you again. I'm sure we'll communicate by email, so thank you both. Goodbye, everyone. Thanks for joining today.